Okay, so we have another calorimeter problem here. This one's going to be a little bit more difficult maybe than the last one. This is a problem that's going to involve looking at heat from two different places in your problem. And over here I drew a calorimeter, kind of just a vague random interpretation of it. Basically what we're looking at, it's going to be a constant pressure because it's open to the atmosphere. Calorimeter, and kind of the intention is, if you can imagine, these solutions are being mixed, grab a pen here, deleted part of it. Those solutions, that's being mixed inside of here, and this is all space all around here. And what that's going to do is basically shield it from the environment, allow the heat of the reaction to be able to be measured without being influenced by the environment. But this problem is going to be a little more difficult because we do have a heat capacity for the calorimeter, and that means it requires 472 joules to raise the temperature of the calorimeter 1 degree Celsius. So that's something we'll need to keep in mind here. So going forward, let's kind of write down what we have. So we have 75 grams of an aqueous solution of lead nitrate being mixed with similar mass, 75 grams of aqueous solution containing sodium iodide, both at the same temperature, which is nice. If you had a problem where they weren't both at the same temperature, probably going to be a good idea to average those two. So add them together, divide by 2, and get an average temperature. That's probably what I would recommend doing. But here, same temperature, so we're fine there. So we'll say mass 1. We're just going to call them mass 1 and 2. They're both 75 grams. Mass 2 is equal to 75 grams. Put an equal sign here. A really sloppy equal sign. And then what else do we know? We know C. This is going to be the heat capacity for the calorimeter. So that's 472 joules per degree Celsius. What else do we know? So we know T1, temperature 1, initial, it's going to be 22.6 degrees Celsius. And the reactants undergo a reaction that raises the temperature to 28.2 degrees Celsius. So we're going to write that here, T2, it's going to be 28.2 degrees Celsius. And we need to calculate the amount of heat generated by the reaction, correcting for the heat absorbed by the calorimeter. So that's an important thing to note here. We're correcting for the heat absorbed by the calorimeter. So that's basically telling you that the calorimeter is going to have some play in this. And we're going to assume that the specific heat of the reaction is the same as water. So specific heat, what is that? That's, as far as our letter goes, we're going to call that S. Water is going to be 4.184, I believe, joules per gram degree Celsius. So what that is the amount of energy in joules. Joules are a unit of energy. It's the amount of energy in joules to raise 1 gram of a substance by 1 degree Celsius. So that is in reference to our solution here. Over here, C, that's our heat capacity. That's of the calorimeter. And so it can be easy to confuse S and C. C is really specific to an object. Doesn't matter how many grams it is. It's this object over here. So there's two relevant equations that then kind of come into play for this. Q is going to be heat. Q is equal to S, our specific heat of the solution, M, the mass of the solution, delta T. That's kind of sloppy. all of this is kind of sloppy. I'm gonna hopefully get better with this tablet as time goes on. And then we have another equation here, which is also Q because we're solving for heat. We have heat in two different sources here. We have heat from our reaction. We also have heat being absorbed by the calorimeter, so we're looking for it in two places. That's going to be C delta T. Simple as that. So this problem, it's not really difficult as far as the math goes. It's just kind of complicated as far as looking at all of your information and knowing what you have. I think it's really helpful to write everything out, so you can see everything put there. And then it's really going to be as simple as adding these two equations together to get Q total for the system, our actual heat generated. So we have our specific heat here, which is 4.184 joules per gram degrees Celsius multiplied by, now keep in mind, it's the total mass of the system. So I have 75 grams of lead nitrate, but I also have 75 grams of sodium iodide. So my total is going to be 150 grams. And that's going to be multiplied by our change in temperature. How are we going to find that change? As is usually the case, delta T is going to be final minus initial. This delta is simply your change. So delta T is going to be equal to 28.2 degrees Celsius minus 22.6 degrees Celsius. So we have delta T. What does that come out to? I believe it's about 5.6 degrees Celsius. Oops. Okay, that is this part right here. We've done this. We still have to do this, and we're adding here C for the reaction, which is 472 joules per degree Celsius, and we're multiplying that, put a degree sign there, by our same 5.6, the change in the temperature. Okay, this is going to be Q. It's a sloppy Q. That's a better Q. Still sloppy. So, at this point, sometimes something I see people mess up with occasionally is this S and this C and where to put it. One thing you can really look at is where your units cancel. So if you were to accidentally switch these, and you know Q is in units of joules, I didn't really need to put that in parentheses there, but just because we're looking at it, just as a reminder, Q is in units of joules. They wouldn't cancel if it was the other way. So what if I wrote it the other way? If I put S where C should be, then I'd have 4.184 joules per gram degrees Celsius multiplied by 5.6 degrees Celsius Celsius cancels, I still have joules per gram. And I have no measurement of grams for the calorimeter in the first place. So the units won't cancel, and you can kind of use that to hopefully guide you when you're looking at it. Remove that. But as it's written here, you'll see, remember, grams and Celsius are in the denominator, which means they will cancel with these. So grams cancels with grams. Celsius cancels with Celsius. We're left with joules. Over here, Celsius cancels with Celsius. And when you get to the very end of all of this, it looks like Q is going to equal 6,157.76 joules. What if that needed to be in kilojoules? Well, there's 1,000 joules is equal to 1 kilojoule. So we can write that to 1 kilojoule, and it's pretty late, so even though that's pretty darn simple to do, it's just moving the decimal over 3 places. Oops, what am I? Yep, see, that's late. Now, I wasn't super great with sig figs throughout this whole problem here. Looks like that would, based off of what we have up here, be about 3 sig figs. So, something like that. And that's going to be solving for the heat of that reaction. So, if this was helpful, click like and subscribe and share it, and we'll put up some more videos.